Hello everyone, thank you for watching my video today on integrating by parts. Up to this point, we have not discussed how to integrate the product of two different transcendental functions. The method that we learned in this section will finally allow us to do this. With it, we'll have the ability to integrate problems such as the three following ones here. Integration by parts is based on the formula of the derivative of a product, which you remember from our unit 3 called the product rule, where our derivative of a product would look like that. Okay, either one of these two, where both u and v are differentiable functions of some variable x. If u prime and v prime are continuous, you can integrate both sides of the equation to obtain this. By rewriting this equation right here, we can find the integral of u dv equals uv minus the integral of v du. A couple guidelines here. First of all, how do I know what to choose for u and for dv? The function piece of the integrand you choose for u should be made according to this mnemonic. U should be a logarithm. If you don't have logarithms, then an inverse trig. If you don't have one of that, then a polynomial, an algebraic. If you don't have one of those, then a regular trig. And if you don't have one of those, then an exponential. Okay, and then the other part would be your dv. Another guideline, just in general, we want dv to be the more complicated portion of the integrand that you know fits a basic integration rule. Then the u would be the remaining portion after that. All right, so let's take a look at our first problem here. Integration by parts. We want to integrate x e to the x dx. So your first thought may be, let's try to substitute for this here. There's nothing we could substitute for that is going to help us out here. We see there's two completely different functions. There's an algebraic and then there's an exponential there. Maybe we can try this by parts. Okay, so there's no logarithm, there's no inverse trig. So that means we probably want our algebraic, our polynomial part to be our u. So let u equal x, and then the rest of it to be our dv. So dv equals e to the x dx. All right, so then du would equal 1 dx, and integrating the dv part, you would get v equals e to the x. So now using this formula right here, the integral of u dv equals uv minus v du. So the integral of u dv equals uv minus the integral of v du. So our answer then would be x e to the x minus the integral of e to the x is e to the x plus c. And here's another one, integration by parts. So again, there's no, our order here is logarithmic would be first, and we do see a logarithmic one here first. So there's no real choice here. You want to start with letting u equal our logarithmic function. And then our dv would be the rest of it. So x squared dx. So our du would be 1 over x dx. Our integral for dv would be v equals 1/3 x cubed, or x cubed over 3. So then our integral is going to be uv, so I'm just going to write that as 1/3 ln x times x cubed minus the integral of v du. Okay, so simplifying this a little bit, we can write this as x cubed ln x over 3 minus 1/3 integral of x squared dx, which is x cubed ln x over 3 minus 1/3 times x cubed over 3 plus c or finally x cubed ln x over 3 minus x cubed over 9 plus c. Third example, an integram with one single term. And another thing to notice here is that this is a definite one. That's not going to change much. It's just at the end we have to substitute our numbers in. So there's no logarithmic here, but there is an inverse trig. So by our rules here, we want to set u equal to arcsine or sine inverse of x, which means dv would be everything that's left, which is just dx. The derivative of u is 1 over root 1 minus x squared dx. The integral of v is just x. So our answer here is going to be uv, which is x, and this is sine inverse of x. There's uv. From 0 to 1. Minus the integral from 0 to 1 of v du. All right, so this first part's pretty easy. We substitute 1 in, we would get 1 times sine inverse of 1 minus 0 times sine inverse of 0. So that's just going to be 1. And the sine inverse of 1, where does the sine equal 1 at? That would be pi over 2 minus 0. So this whole first part is just equal to pi over 2. Okay. Now the second part, we're going to have to use substitution on. So I'm going to let u equal 1 minus x squared. So du equals negative 2x dx. 1 over negative 2 du equals x dx. So minus plus 1/2 integral. We got to change the bounds. We'll do that in a second. 1 over root u du. Put 0 in, we get 1 back. Put 1 in, we get 0 back. So those are our new bounds. We can think of this, I'm not going to rewrite this whole thing here, but we can think of this as u to the negative 1/2, right? So plus 1/2. U to the negative 1/2, if we integrate that, we get u to the 1/2 over 1/2. So 2 u to the 1/2 from 1 to 0. The 1/2 and the 2's cancel out. So it's just plus root 0 minus root 1. So our final answer here is pi over 2 plus root 0, which is 0, minus root 1, which is 1. So pi over 2 minus 1. Number 4, what if we need to use this twice, or 3 times, or 4 times? It can happen. I don't know if we'd ever see one that we'll have to use it more than twice on, but it can happen. All right, so here's another problem where if we try to substitute, nothing's going to help us work. So there's no logs, there's no inverse trig. We're going to let our algebraic here, our polynomial, x squared be u, which means dv must be sine x dx. So du would be 2x dx, and v, the integral of sine, the antiderivative of sine, negative cosine x. Why I put the dx there? Negative cosine x. So I just had to move that over to the side there. Now we can write our first part of this answer as uv, so negative x squared cosine x, minus v du. So it'd be negative cosine x times 2x dx. I'm going to put the negative 2 out here. X cosine x dx. All right, so the reason why we got to do this again is because, again, we have nothing we can substitute for here. We can't integrate as is, and we can't substitute. So we're going to let u equal x and dv equal cosine x dx. So du equals dx, and v equals sine x dx. So now I can write my answer as negative x squared cosine x plus 2 times uv minus the integral of v, I don't know why I put this dx over here again, v du. And now we can do this without any more parts. So 2x sine x minus 2 times the integral of the antiderivative of sine, which is negative cosine, plus c. And there's our antiderivative of our original integrand. Okay, number 5, we're going to look at another method here called the tabular method. This is a great method that saves a lot of time, but it's only something I would use if we're going to pick a u that can derive down to 0 at some point. Can it be used otherwise? Yes, but then there's a bunch of other rules that come into play. So I would only use this method if the u I'm going to pick can at some point be derived down to 0. What do I mean by that? So here's our first problem we're looking at using the tabular method. And you can see I've already set up a table. It's a 3-column table. The first column is a sign of something that's just positive or negative. The second column is the derivatives, and the third column is the integrals. Okay. So in this problem, there's no logs, there's no antiderivative, there's no inverse trig. So I'm going to let u equal x squared. And that's a good thing because that will, at some point, the derivative will be 0. If we keep taking derivatives of that, the derivative will be 0. So that's why I can use this method, which means my dv would be sine x dx. All right, so now we're simply going to do as many lines as we need to until we get 0 in the derivative. So first derivative, second derivative, third derivative. So we've got to match that over here. So the first antiderivative, second antiderivative, third antiderivative. The signs are just simply going to alternate. The first one's positive, and we're going to alternate from there. So our answer is going to look like this. First term, second term, third term. So our final answer here is going to be negative x squared cosine x, positive 2x sine x, plus 2 cosine x, plus c, of course. Let's take a look at another one. So again, there's no logarithms, there's no inverse trig, so I know I'm going to let u equal x cubed, which means I can use this tabular method pretty easily because I know that's going to derive down to 0, which means my dv is going to be e to the 2x dx. Well, I should just write e to the 2x there. Okay, so the sign is going to be positive for that first one. Now let's do our derivatives. It's going to be 3x squared, 6x, 6, and 0. So my antiderivatives are going to be 1/2 e to the 2x. You shouldn't need to do substitution for this by now. You should know the pattern for this. 1/4 e to the 2x, 1/8 e to the 2x, and 1/16 e to the 2x. Signs are going to be negative, positive, negative, positive. So once again, our answer will be these terms here. So my final answer is going to be 1/2 x cubed e to the 2x minus 3/4 x squared e to the 2x plus 6/8 or 3/4 x e to the 2x minus 6/16 or 3/8 e to the 2x plus c. All right, our last one for the notes today. A more difficult integration by parts problem. You'll see why it's more difficult when we get near the end. So first of all, we have no logarithms, no or inverse trig, no algebraic polynomials here. So we're going to want to use u as e to the 3x and dv as cosine x dx. Could you switch the e to the 3x and the cosine x? You probably could. This is just what I'm going to go with for here. So then my derivatives are 3e to the 3x dx, and my antiderivative is going to be sine x. Okay, so my first attempt at the answer here is uv, so e to the 3x sine x minus v du, so 3e to the 3x sine x dx. And as you can see here, that didn't really help. We're pretty much at the same place we started, except we exchanged a cosine for a sine. Let's try it again and see if a second parts will help. So let u equal e to the 3x and dv equal sine x dx. So then du equals 3e to the 3x again, and v equals negative cosine dx. Not dx. I don't know why I keep doing that. Negative cosine of x. So now my answer will be e to the 3x sine x minus 3, and then this is our other parts here, so it's going to be uv, so negative u to negative e to the 3x cosine x minus the integral of v du, so it's going to be negative 3 e to the 3x cosine x dx. There's a dx missing here as well. And we're still not getting anywhere, but we can see, let's distribute here first. So e to the 3x sine x, distribute this negative 3 to both of those. So it's going to be plus 3e to the 3x cosine x minus 9 integral e to the 3x cosine x dx. Remember what this was all equal to. This was equal to our original equation, integral of e to the 3x cosine x dx. And if you see, these two are the same. So I need to combine like terms here. What if I added this 9 over to the other side, and I got 10 integral e to the 3x cosine x dx equals that. Now if I can simply just divide by 10, my final answer would be this over 10 plus c. It's a little bit of combination of calculus and a lot of algebra there as well. Kind of tricky sometimes. That's it for our video today on integration by parts. I hope you enjoyed it. We'll see you again next time.